I thank the organizers for the opportunity to give this talk to close this first part of the conference. When I accepted to participate in the conference, it was at the time it was still going to be a birthday conference for the 6th birthday of Jean-Christophe, and at that time I had the intention to talk about, and I told Sylvain that I would give a talk about his work, and now after it changed, there is it should be discussed at much more detail the work of Jean-Christophe tomorrow in an appropriate setting. So I give a normal talk where I try to make some connection with with some theorem of him. But before I will use a little bit of time to discuss how in many talks, how I met him and his influence on me and the community here. I met him first time in Rio. I don't know exactly when was this because I was a master's student at IMPA, and at that time, I didn't know anything about dynamical systems, and at the same time he was a frequent visitor at IMPA. So it was not going to be an uncommon situation that he would be just in Rio and he would be a common sight at just everywhere at IMPA or at the parties that we had, the barbecues and so on. It took me to the first time that I have a distinct recollection of watching a talk by him was, on the other hand, in 1999 on the Brazilian colloquium. He gave a talk about his work with Yoccoz that to be discussed in part tomorrow. It was work that took a long time. It was very complicated. I got very little mathematically from the talk, if anything. It was the first time that I heard him speak in English. I remember my difficulty to understand his, I was not used to French, and his speaking English looked like he was speaking French, actually, at that time. So I couldn't realize which language was it. And soon after, I had another opportunity. Wellington, my advisor, who unfortunately in this sequence of bad events that we had in the past year, also left us in December, soon after his 70th birthday. We were in our collaboration with Michel Ljubich and Wellington himself and so on. In our paper, it was we had not solved all problems, so it was the paper about regular stochastic dynamics in analytic families of unimodal maps. At that time, that work that would be part of my thesis, it was we had some serious problems that were not solved. We had some partial progress, and I wanted to kind of try to get ideas and expose what we had. And Wellington put me in front of Yoccoz for a very long seminar. And it was the first time that I saw how was it to give a seminar in front of Jean-Christophe, in particular give a seminar about something that you didn't understand completely. So it was very complicated because he managed to find out exactly the points that were kind of a little bit sore in my understanding. So it was my contact with his rigor, and which was at the same time, I at first looked at too strict for me, but with time and learning how to use it in the best possible ways, I realized what was the role that it had in for everybody that would interact with him. So in practice, for the years that would follow, the way people would kind of use his abilities and strictness, and would be to, like, he would give, basically, if you could pass through him with your ideas and so on, you could be very confident that it really worked. So you were kind of unsure about something, and it would be, if you would agree that it is whatever you were doing, it was a proof in his sense, then it's certainly some valid argument. So it was something that was extremely important and very much understood by the community, particularly here in Paris, that he had this kind of sort of role that was a point of reference for the kind of most difficult work being done in dynamics. And he would share his, but of course it was not only rigor that we got from him. He came with many ideas and in many different directions, and was very accessible to people that would come to him. So he would spend a lot of time in his days at the Collège de France receiving visitors that would talk about the project. And I have seen this because I was when I came to Paris, my first opportunity to work, it was him who gave it to me. He gave me he opened a postdoc position in the Collège de France. So for 2 years, I kind of followed a little bit of his routine more closely, and could see people coming and discussing with him their ideas. So usually, sometimes some collaborators, like often. For instance, Stefano and Pierre would come and discuss with him, but often it was just some friends or colleagues that would be there trying to get ideas for their papers, or trying to share what they had, or explain where they were blocked, and he would just talk to them, share the ideas, and he would not become kind of an author of the formal author of the paper. So that's just an important thing to understand about the impact that he had in the community is very far from being measurable by the paper counting or anything like this. It was much more extensive than that. And it was by his questions being asked that he would ask in the seminars that he was running, especially after the death of Michel Herman, and many other influences. So I had the opportunity to collaborate with him a few years after I left my postdoc, and I could enjoy and appreciate better his style of doing math, which was kind of different from what I was more used to for me and for my other co-authors often. And it was kind of always a big pleasure, and it was good to kind of share other experience outside math with him. And there were many in for instance, during conference, as in the Mittag Leffler, and also meeting him several times in Brazil again. And well, just it's clear that his absence will be felt just by is being felt at this moment by the community in Paris, that's still not in dynamics particularly, that still not adapted to not having him around, and more seriously by all his friends in this situation. So thanks. I'm happy to, well, not happy, but it is an honor to be allowed to speak at this moment in his honor. Okay. So I chose a topic that is well, very close to me, and I try to talk about several related objects where the concept of almost reducibility plays a role. Some are better understood than others. Some of the relevance is still not clear. And I start with the one that, with my first contact with the subject, and particularly, and it is the one that I understand better, which is the case of cocycles. So, first contact that I had with this notion was by reading or hearing about results of Akan Eliasson, and so let me put the settings. So they told me to write a pretty large characters, but so the topic is cocycles. So basically, you can have dynamics on the circle. So I'm going to take a simple quasi-periodic cocycles, the simplest kind. So you start with very simple dynamics on the circle, which is just a translation. And on top of that, you construct some fibered dynamical system. So you have add a second variable that behaves, that moves linearly, let us say. So that there is something that depends just on the first coordinate that acts on the second coordinate. What's why you choose, well, it can be, so A of x, here, let me introduce a setting. So x belongs to the circle. And here, the second variable will be acted by matrix, which at this moment will be SL2R matrix. Okay, and you start with this simple dynamical system. It can be seen if you consider y as an element of projective. So instead of looking at the linear action, you consider the projective action. You get some dynamics on the two torus. Now, so you have the circle times the projective, and then you get this two-dimensional dynamics, which is very simple in the first coordinate, slightly, and there may be some nonlinearity in the second, but very restricted. So you have this class of dynamical systems that have been studied a lot. And to this kind of dynamics, you can apply general theory of a diffeomorphism of the torus. And in particular, there is KM theorem. So KM theory would apply if you start in a situation where, let's say, A of x is a rotation. So perhaps in some situation, the dynamics is just, here it could be like y plus beta. So you just have a translation of the two torus in a simple situation. And KM theorem would apply to perturbations of the situation under certain conditions on alpha beta. So basically, this would be, if you understand, so alpha beta, just by general theory, would satisfy arithmetic condition. Condition, you'd have, you can use KM. So KM becomes a good, allows to describe certain perturbations of this dynamic. So you start with this kind of very simple one, and then now you let this kind of get this more general form. And one usual thing that to be used would be that under certain circumstances, this dynamical system can be, you can change coordinates so that it can be seen just as another translation of with maybe the same alpha beta or with some other alpha prime beta prime, also satisfying arithmetic conditions. There is a general theory about that, which as initially worked out, it applies in positive measure set of conditions. So positive measure starts from having initially alpha beta satisfying arithmetic condition, which defines some measurable set, not an open class of conditions. And later on the perturbations, there are also some conditions that must be satisfied. So that's the general setting of KM. And then the theorem that I saw by Akan was a version of this. So the technique was KM, was of KM style, but it was, the result was a little bit different. So what had, so he would assume that, let's say, alpha satisfies arithmetic condition, which we call the Diophantine condition. So, so you have this condition like this, and now you assume that A is not too nonlinear, so A is close to constant. So that's a basic condition of KAM. And then you assume already this. And then he concludes something that's very, so in the statement, so to make the statement, I need something to play a role of beta, but which is valid for any A. So what you can do here is that, of course, in this torus, you have all points are moving in the horizontal direction with speed alpha. And due to the fact that you already have this kind of ordered behavior on the first coordinate, you can make sense of how the rotation happens in the second coordinate. So there's a well-defined as well speed of rotation on the second coordinate. So there is a so-called fibered rotation number. So for cocycles, you can define a fibered rotation number. So you can define this. So just measures the speed of rotation in the second coordinate. And the statement was that if beta, if Ho satisfies some condition, again, so it looks kind of similar, with also arithmetic, which is called some kind of Diophantine condition or rationality with respect to alpha, then the cocycle, which is this dynamical system, is reducible, which means that I can change coordinates so that becomes, it's put in kind of this constant form, so that basically it is, in general, it's the form x goes to x plus alpha, and y goes to a times y with some constant a this time. So, so it looks like just a normal KM theorem, but when you observe here, the condition that's put here is not there is a condition, and he also discussed the need that you cannot get away to get this statement. You cannot get away from putting some condition. But the condition here was a full measure condition. The difference is basically that when you do KM, usually you say, so what's the kind of condition that you have is like how approximation by rational numbers. So you estimate things, and this is kind of the shape of some Diophantine conditions. So to some exponent here. Okay, so that's here, and the conditions like you fix a constant and you fix some r, and then you look at alphas that satisfy this, and this will specify q alpha minus it's big for every pq. Okay. Okay. Okay, so you don't have very good approximations of birational numbers. So this specifies some full measure condition. Once, and then this allows you to fix some kind of distance on which some kind of size of perturbations or that you're going to be able to apply your iterative scheme to get to make the KM machinery work. And the union of all alpha that satisfies such a condition gives the whole Diophantine class, but you have to, usually in the application of KM, you have to first specify, and then you are going to have some epsilon that will be allowed to perturb, and then you continue. And here you don't have this, so you don't have the a priori specification of C and R. You can say, as long as you can find some C and some R, this kind of thing will work. And what was, so it was kind of strange if you're used to the normal, it looked to me a little bit strange if you see the same KM. So how it could work, this proof? What's going on is that usual KAM, what happens that you're going to do a series of conjugations, and that you're going to compose to try to get this kind of final conjugacy at the end. And the series of conjugations, these changes of coordinates, they will converge to some kind of, to this final change of coordinates. And you're going to need several conditions at each stage to be able to compute this change of coordinates, which will give several moments that you're going to use this condition. And what happens in this theorem is that what he was doing is that he was always being able, no matter what, now without any condition on hold, he's able to kind of produce and control the systems enough that he can make a change of coordinates. So he gets a series of change of coordinates always. So his kind of scheme allows to get this change of coordinates that gets you closer and closer to a constant system. So what happens that he changed coordinates here. So you have original system that I write like alpha a of x. It can get a series of chains that conjugates to systems of form, let's say alpha a n of x. And these are getting closer and closer by some change of coordinates here, bn. They get closer and closer to constant here, to some constant. But what happens is that, in general, he cannot say that these bn's are going to converge. His procedure at this level, so here it's converging, but here it could be diverging. And it's under this kind of, just under this condition of the fiber rotation number that he can guarantee that, that the bn's converge as well. So in a sense, so one thing is that he gets always control about everything. Like he is not able to prove that you are actually reducible just because it's not actually true. But he can tell you as much as it's possible about the system, even when you don't know, when you don't satisfy a condition for the fiber rotation number. So it's a very good understanding, which not only from positive measure to full measure, but I would say even it is to everything. Now, everything falls into the analysis, and you're not kind of discarding a priori anything. So it's a big conceptual advancement. And the way that you can think about, so let's give a name to this concept. So it was given, I don't know when the terminology got fixed, but this kind of situation where this may diverge and this is converging to constants, we call almost reducibility. So how you want to think about this concept? It's what are the almost reducible systems? I like to think that suppose that I have some kind of technique that which is like usually KM, but it's a perturbative technique. So I have something that's kind of applies close to constant with some unspecified closeness, like that you depend on several factors. But I know that I have some bunch of techniques that work close to constant. So those are should be thought of as kind of KM methods, even if they come with from different kind of argument. And you'd like to say over which systems those techniques and those estimates that I can get by those methods will be appliable. And the answer would be the almost reducible systems. So you have almost reducible system. The questions that you ask normally, they are invariant by conjugation, right? So if you can conjugate your system arbitrarily close to one that's a perturbative system, to a perturbative situation, arbitrarily close to constant, so at some point you're going to be able to apply whatever techniques and whatever estimates that are only available in principle in that direction. So the class of almost reducible system specifies exactly the reach of the domain of perturbative techniques. So it's something that's interesting to study in itself. And this theorem here says that sometimes this concept gives you some extra and nicer structure, while the KM domain, in principle, like if you specify it too much by the convergence of the whatever algorithm you get and so on, specify some kind of maybe positive or full measure set, but still full with some holes there that miss some kind of generic, bare generic set and, or something. So it's some kind of slightly ugly. We get used to it, but in principle, at the start, it looks a little bit ugly. Now you have such a theorem, which is valid for an open set of conditions. Like forget about alpha at the moment, but alpha is specified, it still remains a whole class of dynamics. Like you get an open set, you can talk about the different A of x that you consider, and now you have a theorem that applies for an open set of dynamical systems, and you can describe all this. So he said that with alpha specified, so let's see a corollary of this, it can be stated as saying that, a nice kind of statement that you get, so fix alpha, right? So then the set of A such that alpha A is almost reducible. So I'm not specifying I should have done, but this is in analytic category, this theorem that I mentioned. Is almost reducible. So that's a natural class to consider. And theorem of Akan says that this is open. Right? So there is all this complexity and so on, and then you get this very nice statement. So things get much cleaner. Okay, so that's this. And then there is a whole bunch of developments around this. So kind of the one theorem that I worked for some long time to get, and in the end it happens, would be this statement here. So that shows that actually it's very nice, this class of this notion of almost reducibility. You get some statement like this. Basically, now more generally, alpha A such that so the set of almost reducible alpha A this is open in appropriate settings. So here is quasi-periodic system, so it can allow alpha to change times the other thing. So, etc. So you get kind of statement that this stability, so this stability property of almost reducible system. So this domain of KEM becomes an open set with respect to all natural parameters that are under consideration. Then you can get a little bit further. So how the theory progresses is so this gives you, so what's at the nature here is that this theorem is just by saying that the content equivalent to that theorem, it's saying that if A is close enough to constant, then alpha A is almost reducible for every alpha. In fact. So there's no restriction on this. So it removes all the Elephantine conditions. So that's the theorem that needs to be proven, that has this implication. So this says that there is a neighborhood of constants that are under control. And then what the theory progresses to see what's actually the reach of this notion, the complete reach of this, what's the best statement that you can have, and so on. And in the end, this led to to get a full understanding of what is can be understood in this of what's this open set. There was the progress towards the almost reducibility conjecture. Okay, so good. Maybe there's an. So this almost reducibility conjecture, so I just wrote here, I continue. So I didn't mention, but not everything is actually almost reducible. So there are obstructions for that, and a good initial dynamic understanding of this kind was very well explained in an important paper of Michel Herman on commentary in the beginning of 80s, relating Lyapunov exponents, and so he was interested in Km theory applied to cocycles, and he was also interested in Lyapunov exponents. So he has interesting things to say about both things. But anyway, there is one concept here that says that, like just to mention quickly, when you iterate this cocycle, the second coordinate keeps being acted by matrix that get in principle more and more complicated. And after you iterate n times, it gets some form that you translate in the first coordinate has just this format, and in the second you get some new matrix. And it's possible that this matrix here, they have, so this cocycle has positive Lyapunov exponent, which means that these matrices have exponential growth. So the Lyapunov exponent that's defined as this limit so this Lyapunov exponent could be positive. And this kind of prevents, for instance, certainly to be conjugate to just a strict rotation. So that creates all sorts of obstructions to be able to have reducibility or anything. So you cannot conjugate it close to a constant rotation, because systems close to a constant rotation cannot have a large Lyapunov exponent. They have to be close to 0. And if it can get arbitrarily close, it has to be 0. So you have obstructions coming from the Lyapunov exponent. And it's true that there are cocycles that are more complicated than just uniformly hyperbolic that have a positive Lyapunov exponent, so-called non-uniformly hyperbolic cocycles. That's discussed, for instance, in this paper of Michel Herman. So what's the class of systems that are almost reducible? So what the topic of that conjecture was to say that all that you need to know is encoded on the Lyapunov exponent. Right? So a necessary condition, if you exclude some kind of simple systems that are uniformly hyperbolic, so that you certainly want to have Lyapunov exponent equals 0 as a condition. Because if you're conjugating closer and closer to constant, let us say, elliptic matrix or parabolic, then the Lyapunov exponent has to be 0. But if you are almost reducible, so what does it mean? So I didn't pay much attention to topology so far, but what does it mean that you have some change of coordinates? So change of coordinates have the following form. So this is a matrix. It's a map to SL2R. And if you work out the form of your change of coordinates, what you're computing, things like this: Bn of x plus alpha, A of x, Bx minus 1. This becomes the new matrix. So this is a change of coordinate. This becomes a new matrix, and it's this that converts to a constant that you want. So you have to apply this. So you have A of x, you try to find some B that makes this exactly equals constant. You actually get a sequence that gets you closer and closer to constant. So the things that you want this to hold so this should hold. So since this analytic maps, the natural thing to ask is that this holds in a fixed neighborhood, in a fixed complex neighborhood of T. So you have this. And okay, so you have this. And what this makes is that, so this constant here has Lyapunov exponent 0, and this constant is constant in the neighborhood of the circle. So in fact, all of this becomes, gets closer. So the Lyapunov exponent is not only 0 when you look at real, for the real variable, but also for the complex variable, as long as the imaginary part is not very large. So you have this, but not only in the real circle, but in a complex neighborhood. Of this circle. So this kind of necessary condition to be in the almost reducible setting. And the theorem that was originally called almost reducible conjecture, now the theorem, it is that this implies almost reducibility. So as long as you have the necessary control about the growth of matrices, that's enough to find changes of coordinates that brings you close to constant. Now, I don't want to discuss about why this is, in all details, why this is so important, but basically it becomes a basic technique to deal with all sorts of problems related to those cocycles. And so the original application was to give a proof that in a very serious sense you can split the cocycles. Like one theorem says that is in a very strong sense the cocycles of zero Lyapunov exponents that you find in one-parameter families, which it's very natural to consider one-parameter families of cocycles here. In a typical one-parameter family, they are all almost reducible. So all cocycles of zero. So either you face the positive Lyapunov exponents and non-uniform hyperbolicity, or you fit into the very nice almost reducibility situation. And this is true not only typically for cocycles, but for all cocycles in a typical one-parameter family. This plays a large role in the main application of cocycles with its the spectral theory of certain Schrödinger operators. So to do this, you need to understand a one-parameter family. So anyway, there are those applications. There are applications about so-called recent work that I have done with Jagong Yu and Chizu, for instance, about the Drayton-Martini problem, which is a statement about so-called certain version of Arnold tongues, or which come from the resonance in certain cocycles, which says that certain Arnold tongues, they don't kind of close themselves too prematurely, and to make the analysis of the whole Arnold tongues, it's exactly a situation where there are several estimates that you come. The estimates that you need are very precise, and they can be obtained using a sophisticated KEM scheme that was prepared especially for this. Not for this, but it was very much developed in this context of cocycles. And but in order to apply them in the largest possible range, you use a preliminary theorem saying that although through this whole range you have some abstract almost reducibility statement, you get somewhere close to constants, and then you apply the perturbed techniques, and then you have your theorem valid, and so on. So there is a certain amount of applications. Okay, so it is a theory that is well established and going. So let's see two different. So where else this kind of notions can be applied? So let me start with first one where I don't know. So let me mention then connection with some work of Jean-Christophe, which I don't know yet how it can be applied to solve some conjectures, but it gives a very nice statement. So the theorem that I'd like to discuss is related to, so there's the book that Jean-Christophe, the asterisk of Jean-Christophe, so with two parts. So most people have seen this important work. So the first part is about the linearization problem for quadratic polynomials and germs of endolomorphic germs, giving a full solution to the Zigio problem. And but there is a second part which is about his work about groups of diffeomorphisms of the circle, which has all sorts. If you go through this, you see all sorts of beautiful theorems, and so he pushed the theory so very far. And later on, probably people didn't think they could do much more than that. So somehow maybe the theorems get kind of hidden there because they appear. If you don't complete the theory, people are kind of incentivate to write many papers and then cite you and use this work as kind of basis. But if you basically close the theory, it becomes kind of a little bit kind of hidden from perspective. It's this case, but it's still kind of a lot of very interesting to read. And one theorem that you can find among the many others is basically the theorem that says that is about conjugacy class. So he's also interested in conjugacy classes of maps. So there is the theorem that he proved, so extending Hermann's theorems over here. So now the setting is, so you have diffeomorphisms of the circle, so f from T to T, which is, so let's say, so it's orientation preserving diffeomorphism. So so it has a rotation number. So there's this notion of rotation number alpha. There is a Hermann-Yoccoz theorem that says that if alpha is Diophantine, then f is linearizable. So I'm assuming here, I work on this infinite category here at first, linearizable, which means that f is conjugated to x to the translation. So you have these. And but what happens if alpha is not Diophantine? Then it's much more complicated. So there are f that are not linearizable. What's so you don't have within this topological conjugacy class of maps with the same rotation number, you don't have a single smooth conjugacy class. You're going to have a complicated structure of all this kind of different smooth classes that are kind of put together. But I proved that the conjugacy class, so for any alpha, so fixed alpha, right? So you'd get some class, let's call A alpha, of maps which is a topological class, all maps that have this rotation number, and you see that in A alpha, the conjugacy class, the smooth conjugacy class, of the rigid translation is dense. So anything, so any diffeomorphisms can be approximated within the topological class by one that's smoothly conjugated to rigid translation. Of course, this theorem is kind of immediate from the linearizability theorem in the case of Diophantine condition, and his work, his additional work, is to prove this in the case of under a Liouville condition, which he proves by a renormalization technique. And this is sort of the opposite to what we're discussing here, because, like, not the opposite, but what we're discussing here, the concept of almost reducibility, is you start with something and you try to conjugate it closer to simpler dynamics. So you'd rather take, instead of approximating someone by someone that's in the class of rotation, you'd like to conjugate your system to something that's close to a rotation. So it's the opposite. So let's say, so you have f here, and you have translation here, right? So this x goes to x plus alpha. Here you have f. So theorem that Yoccoz proved is that there is some f tilde here that is in the class of this rotation. And theorems that you were discussing before is that there is some guy near here that's in the class of f. So it seems like this. So, so what you proved with Raphael Krikorian was exactly this kind of this version here that's inspired by Yoccoz work and his ideas and so on, but focusing on the almost reducibility problem. So the theorem says that any f belonging to A alpha is, so any alpha, any f is almost reducible, or in another way, the topological conjugacy class, the smooth conjugacy class of f accumulates on constant, but you get some kind of nicer statement because since the class of x of the translation accumulates on everything by Yoccoz theorem, so you can rephrase it by saying that the action, the conjugacy action by smooth conjugacies is minimal in A alpha. So all orbits are going to be dense. So that's the theorem. That's a consequence of the almost reducibility of f plus something that you know about translations, which is that you can get closer to anything. So this gives a nice information about this kind of structure of the smooth classes, some kind of additional information. It's always at this point, and as I said, after all this work of Yoccoz and so on, it's difficult to prove something new about the diffeos. So we are happy when you can give some kind of nice statement like this that was not known before. This theorem is proved by renormalization techniques. I'm not going to get too much into, not going to discuss this to any detail, but you have this. Let me mention, so I moved to the smooth category. There is an interesting thing to mention here is that it's not only, why we didn't do it in the analytic category is harder because by the simple reason that it is false, this result. So that should not be understood. There are some difficulties that are kind of serious in this, and then can be understood that in the case of analytic maps, let me, where is the, here. Let me mention this, which allows me to talk about another theorem of Yoccoz. Let me mention. So as you see, Yoccoz proved, gave the optimal condition about linearizability, which was following the work of Michel Hermant, who didn't give the Diophantine condition, but he obtained it later on under the Diophantine condition, a condition for linearizability that cannot be improved in the smooth category. Then he proved something which was so optimal. There is an optimal condition for linearizability, for analytic linearizability. So Hermann found the optimal condition for analytic linearizability by definition. So Hermann at some point said there exists a condition H, which is such that any analytic isomorphism of the circle is linearizable. So that's a good definition. And it is an observation after you have some kind of preliminary theorems that H is not everything and so on. So there are few things that you can say about this condition H. Yoccoz discovered what is the exact arithmetic condition. So now if you have some information about the continued fraction of alpha, then he tells you how to do this. Unfortunately, the condition is very complicated. So there is some precise condition. I'm not going to, I don't remember it. And if I would write it, it would not be very helpful for anybody. But let me mention, what's the flavor of one condition? Let me mention another condition that's kind of very related to analytic problems is the Bruno condition, which is so you have the continued fraction approximants, Pn over Qn, and now you have the lim, so no, not lim. So now you consider this sum. So you do this. So what matters here is some sort of exponential growth here. But you want that, that there's not too much exponential growth, that it goes to 0, and in fact that it goes to 0 a little bit fast, but doesn't need to be too fast. So if this is less than infinity, this is so-called the Bruno condition. And it is what is important, for instance, in the, for the Siegel problem. That's what gives the linearizability of germs, holomorphic germs. And it's important for analytic linearizability. So this is not the H condition, so H condition is more strict than that, but the Bruno condition, so B. So B is optimal condition for local analytic linearizability. So it means that if alpha is Bruno and F is close enough to translation, so the amount of closeness will depend on precise alpha. But so as long as you fix alpha, now you go close enough to rotation, then this is linearizable. It's proved by renormalization, for instance. And what he proved, once he discovered what was the H condition, it follows from his proof, maybe it's possible to do it a little bit simpler, is that 8 is strictly contained in B. Of course, 8 is contained in B, but 8 is strictly is different from B. Right? And now you see that if H, so if you take now F, so if I'm saying that H is different from B, that this means that there exists in particular F, alpha belongs to H, and F belongs to A alpha. No, F belongs to B minus H. F belongs to A alpha, and F is not linearizable, analytically linearizable. Right? And what you can see is that in this case, F is not analytically C omega, let's say, almost reducible. Because if it was analytically, if it was almost reducible, then you could change coordinates and make it become closer and closer to constant. Right? Since it belongs to Bruno, I can eventually apply the local theorem of Yoccoz and get that it is in fact linearizable. So that's not possible. So you see that the problem in analytic category, the notion of almost reducibility, well, so you can invent the notion of almost reducibility, but this, there are things that are just not almost reducible. So understanding of what's the class of almost reducible analytic diffuse is something not completely understood, and this puts a little bit perspective on the fact that this theorem has quite some content on the smooth case. So in the smooth case, it's true, but it's somehow subtle. Okay, so we have this theorem, so it's just kind of nice theorem, and then let me just how much? Okay, so I'm going to discuss quickly now one direction where intermediate, so you have a complete theorem here, you have something here where you have some nice theorem, and maybe it's unclear how to proceed further. There is now a setting where we have some initial theorems, also if Raphael, but we don't know yet where we are going. So we even have a conjecture, but we don't know how to prove it. Well, we know where we want to go, but have no idea how to get there. So we'll give problems to other people also. So it's a setting that I have found very interesting to work recently, which is, so you have a map, let us say, of the disk, so you have F from the disk itself, right? A smooth map, or analytic, or whatever, fixing 0, let's say. Or sometimes I will consider maps of the annulus, fixing here. But it will have a single periodic point. So 0 is the only periodic point. So its orientation preserving here is the only periodic point. In this case here, there will be no periodic point, in fact, so I took out 0. I will assume as well that F is area preserving. So I call this pseudo-rotation. And you try, we would like to understand the dynamics of pseudo-rotations. And there are several theories here. One theorem that we would like to understand is related directly to KM. So let's see. I believe that it should make a nice conjecture. So pseudo-rotation has rotation number. So there is a well-defined rotation number. Alpha, it's irrational. Okay, and a kind of theorem that we would like to that people a kind of conjecture that exists is that, let's say, if alpha, so let's assume F is smooth, if alpha is Diophantine, right? Then in fact this pseudo-rotation. So if F is a pseudo-rotation with rotation number alpha is a translation up to conjugacy, is a rotation. Modulo conjugacy. So that there is not much more flexibility of creating things which have a Diophantine rotation number. If you don't impose a condition of Diophantine rotation number, a pseudo-rotation can be much more complicated. A smooth pseudo-rotation of the disk or the annulus here can be, for instance, weak mixing or things like this. So it's much more, there is a lot of freedom in the Liouville case, but in the case of Diophantine condition, where there is KM theorem, so as long as you have Diophantine condition, you're going to have some control about existence of invariant curves and so on. But the question is near 0, for instance. But the question is kind of getting further away. And then you introduce some kind of a global condition, a control on the dynamics, which means that no periodic orbits appear. And then you get some complete control of the dynamics, theoretically. Okay? And this theorem, this kind of theorem, it's known in perturbative context. So if you're close enough to constant. And what we conjecture, so this is true perturbatively. By Km. Conjecture would be that pseudo-rotations are almost reducible. Which would, so that's a setting where you have an application. If this conjecture is true, you use the local theorem, and then you get this kind of nice rigidity theorem for pseudo-rotations. So that would be nice to have. And what we know to do, so we have progress in this direction, with somewhat analog to one theorem that I stated before about cocycles, which was my earlier theorem about saying that things close to constant are almost reducible for cocycles, so the techniques are completely different. But so the theorem that can prove with Ravel is that if f is so if f is close enough to constant, to translation, so this can be stated for in both settings to a rotation, right? So that so rotation. Then f is almost reducible. Right, so this we have proved. Means that regarding this conjecture here, it's kind of that gives a little bit of improvement, saying that so there is a constant condition, there's the closeness condition that now is no longer dependent on alpha in the Diophantine condition, but it's kind of uniform in this whole class. But we don't think there's need for any condition in fact. But that's what we can prove so far. So we have this this theorem that is proved basically by there are several approaches. You can make a sequence of conjugacies. Probably the best way to look at this theorem is by by controls on the renormalizations. And unfortunately, to have control on the renormalization, you start assuming that you are not too far from a constant, and then you renormalize, and you guarantee that this condition is still satisfied. But what is so this is an approach general even for alternative to KEM and so on. So what's new here is to be able to make, so the situations like you have this kind of map, and you have this dynamics, and how to kind of manage to do a renormalization procedure with some control, assuming that you don't have too much nonlinearity, or nonlinearity bounded by, let's say, 1/10 or whatever. It's not extremely small, but it's kind of still bounded by 1/10. So you have this, suppose this condition, and but now you don't have much assumption on alpha. So the bad situation is not alpha. You assume that's extremely close to 0. Right? So you're just translating a little bit. And to renormalize, you have to, of course, iterate by more or less 1/alpha to make the first renormalization, right? So in this situation, you're going to iterate a long time, and in principle, you should lose control. And somehow, we managed to make some vector field approximation of this dynamics by using so-called an a priori estimate that comes from some general reasoning which kind of exposed in a paper with, so it's my paper with, so let's, since many authors I write here, so now, so it's with Bassan and Patrice, and now how Shengshu and Ziyuan Zhang. So there is this theorem that that contains a kind of nice analysis about showing that analytic diffeomorphism of the disk volume preserving cannot be mixing. So there is a theorem of independent some other theorem, but there is some discussion here which is closer to here, because you quickly get into the setting of pseudo rotations. And the point here is that there is an estimate that says that if alpha, so it's interesting estimate when alpha is small, that says that if you have a pseudo rotation, so no periodic orbs appear with rotation number alpha, then you have an estimate here that you have a disk, and you have a small disk here, and let's assume that this small disk doesn't intersect itself by one iterate. It's a very simple thing. So that's by F. So it's in the case here. Then the area of the disk is smaller than alpha. I think that's correct. The estimate. So it says that if this rotation number is very small, then the only way that you don't intersect is by taking an extremely small disk. So this limits the fact that things have to come closer together under iterations. Alpha is small, and this is uniform here for all disks. And this is what comes into to make an analysis of the vector field approximation and a little bit about the dynamics of the vector field. This allows you to control this iterate and do a first normalization, and then you get in the setup that this can be continued. The analysis is kind of not very easy, but here, I just wanted to mention one additional ingredient that appears. So this is true in general, right? What's additional is, like, just to make the initial vector field approximation, you need also to assume that things were not too large to begin with. So this is unfortunate, and we don't know. But we kind of believe really that the conjecture is true, and you see that it should give a very nice description of this whole setting of pseudo-rotations. And anyway, it was basically an advertisement for this notion of almost reducibility, and I hope that it will appear in other contexts as well and be applied to some good use.